Welcome back to the Deep Dive. We've got a really interesting challenge from you today.
That's right.
We're diving straight into the Feynman Lectures on Physics, Chapter 50, the topic, Harmonics.
Yep. And our goal is really to unpack the core ideas, the intuition behind the math. Why do musical notes sound the way they do?
Right, how does all that quality and periodicity actually work? Feynman starts us off way back, doesn't he? Like ancient Greece.
He does, with Pythagoras, which might surprise some people. We think geometry. But Feynman points out this amazing discovery about music.
About vibrating strings.
Exactly. Around 500 BC, Pythagoras figured out that the musical intervals we find pleasing, the octave, the fifth, the fourth, they correspond perfectly to simple integer ratios of string lengths.
Okay, so like if you have the string length,
You get the octave, that's a 1.2 ratio.
and 2/3 of the length gives you the fifth,
Yeah,
a 2.3 ratio.
precisely. It was this incredible finding that something subjective, like pleasing sounds, was directly tied to simple numbers, a quantitative relationship.
Feynman mentions this sort of spun off into mysticism, the music of the spheres and all that.
Yeah, it did, unfortunately. But the core discovery, that was, as Feynman puts it, a really early success for quantitative science. Real physics based on measurement.
Okay, so that sets the stage. But let's define our terms. What is a musical tone, physically speaking? How's it different from just noise?
Good question. If you were to graph the air pressure hitting your eardrum over time, noise would look totally random, all jumbled up.
No pattern.
Right, but a musical tone, it's periodic. The pattern repeats exactly, over and over again. Think of a wave shape that just keeps cycling.
And that repeating wave has key features.
Three main ones. First, how fast it repeats, that's the pitch, or the frequency.
Higher frequency, higher pitch.
Correct. Second, how big the pressure changes are, the peaks and troughs of the wave, that's its loudness or amplitude.
Makes sense. And the third one is the tricky one.
That's quality, or timbre. It's the specific shape of that repeating wave pattern. That's what makes a violin sound different from a flute, even at the same pitch and loudness.
So all that richness or raspiness is just the wave's particular shape. How does one string make such a complex shape, not just a smooth up and down wave?
Because the string doesn't just vibrate as a whole, it vibrates in multiple ways at once. These are called its normal modes.
Okay.
So the string vibrates along its full length, that's the main frequency, the fundamental, let's call it mega dollar dollars. But it also vibrates in 2/2 and 3/3, 4/4, and so on, all at the same time.
Okay. Those are the overtones or harmonic.
Exactly the same thing, harmonics. And they're simple integer multiples of that fundamental frequency. 2 mega dollars, 3 mega, 4 mega, and onwards. The sound you actually hear is the sum of all these simpler vibrations.
Which leads us right into the main event, the Fourier series. What's the big idea here?
The big idea is, well, kind of mind-blowing, actually. Fourier's principle says that any repeating periodic wave shape, no matter how complicated or jagged it looks,
Yeah.
can be perfectly built just by adding together a potentially infinite series of simple sine and cosine waves.
Seriously. Any shape.
Any periodic shape. You just need the right combination of the fundamental frequency and all its integer harmonics.
It sounds like a recipe. Like the final sound is the cake and the harmonics are the ingredients. Can you describe the formula conceptually?
Yeah. Think of it like this. Your final complex wave, phi t, is equal to some constant average value, let's call it $t, plus a sum.
A sum of.
A sum of all the harmonics. For each harmonic number n, like 1, 2, 3, you add a cosine wave part and a sine wave part. Each of these parts has its own amount or amplitude, these coefficients on dollars.
So the un tells you how much of the n the cosine wave to add, and the dollar tells you how much of the n sine wave.
Precisely. And those amounts, the sizes of all the different ons and amateurs, that is what defines the quality, the timbre of the sound. It's the mathematical recipe.
Okay, I think I get it. So a flute sounds pure because
Because its recipe is simple, it's mostly the fundamental frequency, maybe a tiny bit of the second harmonic. So a $1 and maybe B dollars are big, but all the other on and Botter's dollars for NA2, 3, 4 are very small.
whereas a trumpet or violin.
Much richer. They have significant amounts larger NE2 ladders for many of the higher harmonics. That's what gives their sound that complex, bright, or maybe even slightly buzzy quality. It makes the wave shape more intricate.
And you mentioned this applies to speech too, how we make vowel sounds.
Absolutely. Your vocal cords produce a basic buzz, rich in harmonics. Then your mouth, your throat, your tongue position, they act like filters
That there's four.
for the harmonics. When you shape your mouth to say E versus A, you're emphasizing some harmonics and damping others down. The fundamental pitch might stay the same, but changing the harmonic recipe creates those distinct vowel sounds.
Fascinating. Okay, let's just quickly revisit Pythagoras and those perfect ratios. We know 3.2 sounds great, but pianos aren't tuned exactly that way, right? Why not?
It's a practical compromise. If you tune everything using those pure, perfect ratios, an instrument sounds fantastic in maybe one specific musical key.
But if you change keys,
Things start to sound slightly off. The perfect ratios don't quite mesh perfectly when you shift the starting point. It's a mathematical quirk.
so pianos use, what's it called? Tempered tuning.
Exactly. Tempered tuning adjusts those intervals just a tiny bit away from perfect purity. It spreads the slight out-of-tuneness evenly across all keys, making the instrument usable no matter what key you play in. A small sacrifice in purity for versatility.
Right, makes sense. Okay, now the really clever part. We know how to build a sound from harmonics if we have the recipe, the coefficients, 1 to B and B and O. But how do we work backward? If I give you a recording of a sound, how do you figure out its recipe? How do you find those coefficients?
This is where the mathematical magic really shines. It relies on a property called orthogonality.
Orthogonality. Sounds complicated.
The name is maybe a bit intimidating, but the idea behind it is surprisingly neat.
Okay, walk me through it. Let's say I have this complex sound wave recording. I want to know exactly how much of the, say, third harmonics cosine wave, ATT's in there. How do I isolate just that one piece?
It's like having a magic filter. You take your entire complex sound wave over one full period,
Yeah.
and you multiply it point by a pure cosine wave of exactly the frequency you're interested in. So in your case, you'd multiply by OP2.
Okay, multiply the whole messy wave by the clean third harmonic cosine. Then what?
Then you calculate the average value of that product over one whole period. And here's the trick. Because of orthogonality, when you do this multiplication and averaging, all the other harmonic components in the original sound, the fundamental, the second harmonic, the fourth, all the sine parts, they all average out to exactly 0. They cancel out.
Whoa. So multiplying by a toy-T acts like a filter that only lets the 333 parts survive the averaging process.
That's exactly it. The only thing left after averaging is a number directly proportional to 33/30s. You do the same trick, multiplying by sinus to find 33/30s, and you just repeat for every harmonic number and you care about.
That's incredibly elegant. It lets you pick apart the sound, harmonic by harmonic.
It really is. Feynman uses the square wave example to show this.
Right, the one at the sharp edges.
Yes. To build that sharp, sudden, up and down shape, the Fourier analysis shows you need only the odd-numbered harmonics 1, 3, 5, 7, and so on. And it tells you precisely how much of each you need, with the amounts dropping off in a specific way to make those sharp corners.
And there's a connection to energy, too.
Yep, the energy theorem. Basically, it says the total energy in the waves, which is related to the average of the waves' values squared, is just the sum of the energies of all the individual harmonic components. It's proportional to the sum of N2 ops plus Bn2 DAs for all the harmonics. Energy adds up simply.
Okay, so far this is all very neat and tidy. Everything adds up nicely. Linear superposition works perfectly. But then Feynman throws a curveball. Non-linearity.
And this is crucial, because the real world isn't always perfectly linear, especially when things get intense. Linearity means output is directly proportional to input. Double the input, double the output.
But nonlinear means?
Nonlinear means that relationship breaks down. Maybe the output involves the input squared or cubed or some other more complex function. $6 not just times $6.
What happens mathematically when you put a simple sound into a nonlinear system? Let's use Feynman's simple case. Output, co-Nidal's input, plus epsilon times input to the 2.
Okay, so if you feed just a pure cosine wave, Feynman to that system with the squared term.
Yeah.
2 completely new things pop out. First, because you're squaring the input, which goes positive and negative, the output squared is always positive. This creates a constant average value shift upwards. It's called rectification.
Rectification.
Yeah.
Like it's turning the AC wave partly into DC.
Yeah.
Pushing the average up from 0.
Sort of, yeah. It creates a steady component related to the intensity or energy of the input wave.
Interesting. What's the second effect?
The squared term also generates the second harmonic. Your input was pure megaTs, but the output now contains a piece that varies as megaT.
So a pure tone going through a slightly nonlinear device automatically becomes complex. It creates its own overtone.
Instantly. And it gets even wilder if you put 2 pure tones in, say a megator 1 and a megator 2.
What happens then?
That squared term causes them to mix. The output will contain the original omega tall or omega 2 their harmonics, like 2 omega 1 and 2 omega 2 does, and the sum frequency, omega 2 plus omega 2, and the difference frequency, omega 1 2. These new frequencies are generated purely by the nonlinearity. This is called modulation.
Modulation. Okay, that sounds important technologically.
Hugely important. AM radio is built on this. Your voice is a low frequency. The radio station's carrier wave is a high frequency. A nonlinear circuit, the modulator, mixes them to create sum and difference frequencies that can be broadcast effectively.
So nonlinearity isn't just noise, it's actually useful.
Absolutely essential in many cases. And Feynman points out it happens in biology too. Our ears are thought to behave nonlinearly, especially with loud sounds.
Generating extra harmonics or those sum and difference tones inside our own hearing system.
Exactly. It might contribute to how we perceive consonance and dissonance, especially at high volumes. And the same physics, remarkably, applies to light.
Light. How so?
For a long time, light interacting with matter like glass was thought to be perfectly linear. But with intense light, like from modern lasers, the materials respond nonlinearly.
And
You can get the second harmonic of light. You shine intense red laser light into the right crystal, and out comes some green light double the frequency. It's a direct result of that 622 type of nonlinearity.
wow. Okay, let's try and pull this all together. We started with Pythagoras finding simple number ratios in music.
Right, the first quantitative connection.
Then Fourier showed us that any repeating sounds quality, its timbre, is just a sum of simple sine and cosine harmonics, a perfectly linear addition.
The recipe book for sound quality.
But then we hit the real world, where high intensity leads to nonlinearity. And that nonlinearity breaks the simple addition rule.
And actually creates new frequencies, harmonics, sums, differences that weren't there to begin with. It's the basis for modulation and effects we see even in light.
It really drives home that the beautiful, simple linear physics, like Fourier analysis, is often an approximation. It works perfectly when things are gentle, low amplitude.
That's a great way to put it. Linearity is often the low intensity limit. Sound is linear at low volumes. Feynman makes the point that for light, people assumed linearity for ages until lasers got powerful enough to reveal the nonlinear effects.
Which leaves us with a pretty interesting final thought, doesn't it? If simple superposition, this idea that effects just add up, breaks down when you push systems harder.
Yeah.
And those breakdowns, the nonlinearities, are what enable things like radio communication and creating new colors of light. Well, what other fundamental physics might just be waiting for us to crank up the intensity and see what new rules emerge?
That's a fantastic question. What happens when we push other systems far from equilibrium? It's where a lot of modern physics happens.
Indeed. Well, thank you for taking us through this deep dive into the physics of sound, from ancient strings to modern lasers.
My pleasure. Hopefully you hear the world a little differently now, maybe pick out some of those hidden harmonics.